Everyone, welcome to Data 100 Discussion 11. My name is Jake, and today we will be going over problem 2 of the Discussion 11 worksheet. And specifically, problem 2 is all about inference. And the tool we're going to be using to perform inference in this worksheet is called the bootstrap. You guys, maybe you have seen the bootstrap before in Data 8 or some other statistics classes, but the bootstrap is a really popular and useful tool for essentially giving us an idea of the sampling distribution. And when I say sampling distribution of some estimate, all I mean is it can give us an idea of what we should expect an estimate to be, essentially. Okay, so in that whole idea will become more clear as we get into the problem. Okay, so let's get going with problem 2. So in problem 2, we assume we have a simple linear regression model, which is given by y equals theta 0 plus theta 1x plus epsilon. Y is our response, x is our design matrix with all of our data, and epsilon is our noise, or our error. In this problem, we want to use the bootstrap to compute a 95% confidence interval for, it says theta hat here, but we really want to compute the 95% confidence interval for theta 1 hat. You could bootstrap to find a confidence interval for theta 0 hat, but the intercept is typically less interesting, and normally we're more interested in this slope. So this really should say theta 1 hat. Sorry about the small typo. Okay, so what we want to do, I'll just type it here, is we want to create a 95% confidence interval. I'll just say CI in the future for our slope coefficient. And the bootstrap is going to be the tool we use to go about creating this confidence interval. And so really what the idea of the bootstrap is, let's go ahead and see. Just do another text box. So the idea of the bootstrap is we have some kind of population of interest, right? And we want to make some kind of inference or learn something about this population of interest. And so what the bootstrap is going to exploit is it's going to say, okay, we have this population of interest. We obviously can't collect a census of this population, or we can't collect a sample of this entire population. So instead, we're going to go off and we have to we have to take a sample of this population. And the bootstrap it's important to understand conceptually. Yeah, let me just also put bootstrap procedure here. This is all about the bootstrap. So once we have this sample of this taken from this population, with the bootstrap, it's very important that this sample is representative of our population. Because what we're going to be doing with the bootstrap is we're going to be using this sample to create a bunch of other samples. So from here, and this is where the bootstrap really comes into play, is we generate many new samples from this original sample. And a typical number of samples that we'll generate, we'll say, is maybe b equals 10,000. This is just some theory that some statisticians have decided is generally a good number of samples to take. And for each, the idea is, this basically means we have 10,000 new samples that we drew or that we generated from this original sample. And so the next idea is we calculate our estimate or statistic of interest for each of these 10,000 bootstrap samples. Go ahead and move this where we can see it. So this arrow isn't exactly great, so we'll just draw it like that. So we have these 10,000 bootstrap samples. And in our case, since we're interested in this slope coefficient, from our 10,000 new bootstrap samples, we're going to calculate a slope coefficient. So we're going to end up with 10,000 new slope coefficients, and that is going to be how we generate our confidence interval. And so this is kind of the general procedure. And now part A says use a box model to describe the process of computing this 95% confidence interval for theta 1 hat. So let's go ahead and do that now. I might end up scrolling past this, but that's okay. So here we'll say this is 2A. And so box model, right? So this is the idea of a box model. So here we have our population. And we'll say it has size big N. And basically all this is, in this context, is it's a collection of tuples of information. Remember, we're doing simple linear regression, and so there's only one predictor x associated with its label y, xn, yn. So this is our population of size n here. And so kind of following this procedure I was discussing above, what we do from this step is draw a little arrow here. We are going to let's do another box. Take a sample, and we'll say this sample has size little n. And so all this gives us, in the context of this problem, is x1, y1 pairs up to x little n, y little n. And so remember, little n will be smaller than big N. And so here with this sample, we have less data. We don't have access to this entire population. And so as I was saying before, it's very important that before we try to perform inference or the bootstrap or anything like that, it's important that we have reason to believe that this sample that we take here is representative of our entire population. And from this point on, once we have this sample of size n, we can really get into the bootstrap. I just realized I can maybe do some arrows here. So how the bootstrap is going to work is, remember, we have to generate some new samples, and I'm going to kind of formalize that in a minute. Okay, let's see. Just make some new arrows here. Excellent. And so the idea of the bootstrap is, I can get my pen. Right? So the idea with the bootstrap is we're going to take this sample and generate, we'll say, again, we'll go with B equals 10,000 new samples. We'll call them bootstrap samples. So generate B equals 10,000 new samples called bootstrap samples from our sample drawn with replacement. And so it is very important that we draw these, you can imagine 10,000 of these boxes, 10,000 samples with replacement from here. And so what happens is, the idea is that, okay, some of these boxes, you might include some points multiple times, but that's okay because they'll all average out to across like 10,000 replications or 10,000 of these samples. Each point, the idea is each point will have about roughly equal representation overall. So do make sure that we remember that these samples should be drawn with replacement. That's a key element of the bootstrap. So for example, here in this, we might get x1, y1. We might get x1, y1 again. And here we'll say like we get the last data point, x and y in. So I just remembered I can't forget this, that these 10,000 new samples are of size n. So these bootstrap samples are of the same size as our original sample. Maybe we'll just say original sample here, just to make that crystal clear. This is our original sample, and these bootstrap samples must be of the same size as our original sample. So for example, we could maybe here we get like x2, y2, ... We'll say maybe x500, y500. And you can imagine that there's little n number of these samples in this box. Similarly for here, we could get x4, y4, x5, y5, and then we could get x4, y4 again, amongst others. So this is kind of the idea. And so, yeah, okay, so this looks good. And so we have these 10,000 bootstrap samples. And basically, in the context of this problem, we can think of these, we think of each of these bootstrap samples as a data set, right? And so when we do this, it's pretty easy with this in mind that we can calculate a slope coefficient for each of these 10,000 data sets. So remember, we have 10,000 bootstrap. We can say data sets now. And for each of these data sets, we will compute a slope coefficient, and we'll call it, maybe I'll just draw it because I can't really write LaTeX or anything here. So we will compute a slope coefficient of theta. Sorry if this is, remember we want our slope coefficient for theta 1, and we'll say theta 1 b. And so remember, this b is not an exponent, right? So for example, what I mean by this is, if this right here, we say is our first bootstrap data set, then for this data set, we calculate, is this working? Yeah, it is. We calculate theta 1, 1. And here, we will say we calculate theta 1, 2. All the way up to theta hat, because this is an estimate. We'll say, in this case, we say b is 10,000. So here we would have like theta 1 hat, 10,000. And so in this way, we can calculate 10,000 different estimates for theta 1 hat. And now we kind of get to the crux of the question, which is asking, okay, so given that we slope coefficient estimates, how do we calculate a 95% confidence interval for the slope coefficient? And this is actually pretty simple. All we're going to do is we're going to line up our estimates from smallest to largest, right? So you can imagine taking theta hat 1, the first one, and then the second one, all the way up through the 10,000th, and we're going to line them up from smallest to largest. And once we do that, we pick the, I'll say 2.5th percentile as the lower bound for our confidence interval, and the 97.5th percentile as the upper bound for our CI. And this is a 95% confidence interval because remember the definition of percentile. This is important. So the 2.5th percentile is the value, the estimate, such that 2.5% of all of the estimates lie below that value. And similarly for the 97.5th percentile. So this percentile will give us the theta, the estimate, such that 97.5% of all estimates lie below this one. And so this is a 95% confidence interval. You can think of intuitively because we're leaving out 2.5 on the bottom, and we're leaving out 2.5 on the top. Okay, so this is our way of capturing the middle 95% of all of our estimates. So I guess in conclusion, our CI is this interval 2.5th percentile of our, and I guess maybe so we can be clear, this is our, we'll call this like the Beath, the Beath slope coefficient bootstrap estimate. So our CI is the 2.5th percentile of our bootstrap, of our slope coefficient bootstrap estimate, comma, 97.5th, this is hard to say, of our slope coefficient bootstrap estimates. And this is all we'd have to do to calculate a 95% confidence interval for theta 1 hat. And so this is the answer to part A. Okay, great. So part B says, now that you have some intuition for how the bootstrap works in a simple linear regression setting, let's think about how we might do this for multivariate linear regression. So remember, in multivariate linear regression, we just have our model given by, we include a bunch of predictors, and therefore we have more than one basically slope coefficient. And here again, our idea is we would like to generate confidence intervals around our estimates of theta. And so this question says, outline in pseudocode a non-parametric bootstrap-based approach to find a 95% confidence interval around each theta I. And we assume that there are n data points. And so, okay. And the way we're going to kind of attack this is we'll attack this from kind of a vectorized point of view. You can imagine we work with a lot of vectorization in NumPy and in pandas, and that's kind of the approach that we'll be taking here. So basically we're just going to generalize what we've done above into this problem here. So let's say this is 2b, and we need to, why did that 2 go away? 2b. We need to write some pseudocode for 95% CIs in multivariate linear regression. And okay, so let's think about how we might want to do this. So the first kind of idea that comes to mind is we need some kind of container. So we'll say we need some kind of container to store our, we'll call each of these, we'll say these are like our theta i's. So we need a container to store our theta I. We'll say theta I hats because they are estimates, remember. Okay, so in code this might look like, okay, theta I hats. This is just going to auto capitalize, I guess, unfortunately. We'll say let's make some kind of list, and the list will be our container to store our theta I hats. And remember, the next idea is from above, we need to generate, for example, generate b equals 10,000 new samples of size n. And I guess I maybe should have said this earlier, but we are imagining that our data set that we're given is our sample, right? So we're not imagining that the data set we have is this population. Remember, we just basically never have access to this entire population of information. So this data set used to generate this model is this original sample. So given that, the next step is to generate b equals 10,000 new samples or of size n. This should not be r. And these are our bootstrap samples. So one way you might say, we can set b equal to 10,000, but I'll put a little comment here. You can pick really any b that's large. It's just that 10,000 has theoretically been shown to give good results. So once we set this, we can actually go ahead and start thinking about generating our b bootstrap samples. And so in code, this might look like, okay, so we'll say for I in, oh no. Okay, so we'll say for k, we'll say k is kind of like our indexer in range b, right? So this is going to give us a way of looping through 10,000 times, and we need to create a bootstrap sample at each iteration. So we'll say our boot sample, this is bootstrap sample, is sample. Here I'll say with replacement. Remember, in the bootstrap we draw with replacement, and we'll give it our data. And we need these samples. Remember, we need these samples to be of size n. So here, for each bootstrap sample, we're taking a sample with replacement from our original data set, also known as our original sample of size n. And the next step is, once we have all of our 10,000 or whatever b is, that number of bootstrap samples, we need to calculate, instead of just a single slope coefficient this time, here we need to calculate theta 1 hat, theta 2 hat, theta p hat, so p slope coefficients. And so the way to do this is just perform, we'll say multivariate linear regression on the bootstrap sample. The bootstrap sample. And so what we here say is, we'll say like our theta hats for this kth iteration is equal to, we'll say we want some linear model of our boot sample. So here we're going to say we have some boot sample, and generally you'd have to break this up into x and y, but this is pseudocode, boot sample, and we'll say like this linear model has some coefficients attribute that we can access to give us these p coefficients here. Perfect. And so here, now that we have these theta hats, we need to say theta I hats dot append theta hats. So all this step is doing is just appending estimates at kth iteration to our container. And this is almost all done. Here, maybe I can get rid of some of these red lines because I imagine that might make it hard to read. Let me go ahead and do that. Let's go ahead and ignore all of these. Sorry about kind of some of these annoyances. It's just, I wish I had a better way to do this, but it's how it's going to be, I guess. And so at this point, let's kind of take stock of what we've done. We have a list of B theta I coefficients. And this is kind of where the vectorization thing I was talking about comes in. So we know that kind of the first entry of this theta I hats is going to be theta hat 1, theta hat 2, all the way up to theta hat p. And then the second entry is going to be the same thing. Obviously the numbers will be different, but the ordering will be theta hat 1 comes first for each set of thetas. And so all I'll say here is imagine we'll say each theta I is lined up in order as I was talking about here. So we'll imagine that each theta I is lined up in order. This is pseudocode, so kind of casual. Don't worry too much about the details. But all we need to do here is we need to percentile is, remember, we need the 2.5th percentile, however you want to say it. So we'll make a variable called that is our percentile from our theta hats, and this will get us the 2.5th percentile here. Let me go ahead and ignore these. And then we need 0.975 percentile will be the 97.5 percentile. Theta hats and then if you wanted to, so these get us the percentiles we need. If you wanted to say, let's print out the CIs, we could say our final confidence intervals are kind of like these two element lists. And so that is it. That's it for the bootstrap, and that's it for the pseudocode. Hopefully this whole process makes sense, and I hope it's clear that the pseudocode from 2B is really just a generalization of what we did in 2A. And if any of this is not clear, of course feel free to ask on Piazza. And I thought maybe it might be useful to show you all some image just to kind of get a visual of what the bootstrap is doing. And so let's go ahead and take a look at this image here. So this is the last thing. So here on the left, we have this was a histogram. This is, some distribution we can imagine of a statistic alpha. In this case, our statistic was, these slope coefficients here. But this is just something I got out of a stats textbook. And so they're showing their statistic of interest is this alpha. And so what they did to make this histogram here was they took they took a bunch of data sets. We could say 10,000 individual data sets from some population, and they calculated alpha. And this is the histogram they got. And then here, the blue histogram we have is they just took one single data set from the population, and then they did the bootstrap. They said, okay, we'll take that one single data set, we'll calculate 10,000 new data sets sampled with replacement, as we were talking about, and we'll calculate an alpha for each of those 10,000 bootstrap data sets. And this is the histogram they got. And you can see that it's actually very, very similar to this yellow histogram, in which they just had 10,000 separate data sets or whatever from the population. And so the whole point of me showing this is just to show that the bootstrap, remember, as long as the bootstrap, as your original sample is representative of the population, bootstrapping can actually give you a very close approximation. And so these distributions are almost the same, and these alpha values are really close as well. And here on the right, this is just showing the same thing, but for a box plot. And so I hope this kind of gives you all maybe a more geometric understanding of what's happening with the bootstrap, and just showing that the bootstrap can be really useful. Remember, we would like to always do something like this, where we just had a bunch of different data sets from a population. But generally we don't. We just have one data set, and we have to do the best we can. And so bootstrapping can be a really good way to create a good approximation. And I think that is it for this question. Feel free to post on Piazza if you have any questions, and we'll be happy to help. All right, thanks for watching, and good luck with the rest of the discussion. Bye.